So the first thing we're going to need to do is draw a figure. And so we have an outer cylinder, and then we have an inner cylinder. The outer cylinder does not move, but the inner cylinder rotates. That is going to be the important part of this problem. Then we can also draw a top-down view of the Couette cell. And so we're going to extract a few variables to use in the equation. So we're going to take the height of the inner cylinder. We're going to take the radius of the inner cylinder and the radius of the outer cylinder, and we need to find angular frequency. And the way we can do that, we can take tangential velocity on any point of the inner cylinder, but that equals v. So we're going to need to use an expression with angular frequency, rearrange that, and when we do that, we get omega times inner radius. So with torque, we can use an expression. It goes like this: torque will equal viscosity times sigma. Sigma in this case will equal shear rate, and torque in this case is also equal to shear stress. I don't know why I wrote it like that. Shear stress. And then shear stress is equal to force over area. Now force in this case, we want force in terms of torque, and like we did with this tangential velocity, we're going to need to put it in terms of torque. So using a similar concept, there's an equation for torque with force and a radius, and using that equation we can rearrange the equation and get force is equal to torque times inner radius, again since we're measuring the speed or force in this case of the inner radius, or inner cylinder I mean. And then for area, we're mainly focused on the wall of this inner cylinder, and the expression for that would be 2 pi r times that by h. And so we can rewrite that initial expression we wrote. This will be Ri. And so we can also modify this side of the equation. So viscosity will stay the same. And then we'll change shear rate. The top of the fraction will be dv theta. Bottom will be dr. Now dv theta will be equal to the tangential velocity, but we're going to use this formula / expression that we found. So we will replace dv theta with omega radius inner, then dr will just be the space between the inner cylinder and outer cylinder. We can write that as r outer minus r inner, then just copy the rest of the expression. At this point we can just rearrange the equation to find the viscosity. So first we can cancel those two, then I'm just going to write viscosity right here, multiply both sides by r outer minus r inner. So we got that done. We can also divide both sides by omega Ri. Let's make sure we got everything. Let's see, 2 pi. Whoops, no, that's not supposed to be it. This is supposed to be h, not ri, because we canceled that out already. So 2 pi h omega ri. Yes, so this right here will be the final expression for the viscosity of the fluid in a Couette cell.